To violently vaporize a microscopic solid target in industrial applications, an optical system must deliver extreme peak power. Standard continuous wave lasers, like a typical ND-YAG system, max out their average output at around a few hundred watts. Continuous wave power is measured in watts, but advanced applications demand peak powers in the terawatts. We cannot achieve this by simply increasing pump power. Instead, we manipulate the optical resonator to compress light into a microscopic sliver of time, or across the frequency domain. Generating the highest energies in optical physics is a problem of architectural timing rather than raw power generation. To understand this timing, we start with the basic mechanism of optical pumping within a 4-level active medium. This diagram shows a 4-level energy model. Electrons transition from ground state N0 to upper state N3, then drop to metastable state N2, building a population inversion. Between the resonator mirrors, bouncing photons strike these particles, forcing them down and emitting duplicate waves. This system eventually reaches a strict mathematical limit, the state where the gain multiplied by the loss equals exactly 1. Because the photon density always rises to meet and consume the population inversion, a continuous wave system physically cannot store massive amounts of energy. How do we prevent the photon field from consuming that population inversion before it reaches extreme levels? We use active quality, or Q modulation. This means temporarily degrading the resonator's feedback loop. By placing an opaque block in front of one mirror, the cavity's Q factor drops and bouncing light waves vanish. With the cavity off, the N2 population inversion climbs exponentially past normal thresholds. Removing the block restores the cavity, triggering an immediate light avalanche. QSwitching deliberately weaponizes the laser medium's capacity for energy storage, trading a continuous output for a single nanosecond burst. Mechanical shutters are entirely too slow to switch a cavity on and off in the required nanosecond timeframe. We solve this with an electro-optic approach for an ND-YAG laser. Component 1 is a Brewster window, filtering light so only linear polarization passes freely. Component K is the Pockle cell, containing a crystal that alters light polarization when high voltage is applied. The beam enters linearly polarized. The active Pockle cell makes it circular. The mirror reflects it back, and the second pass through the cell rotates the original linear polarization by 90 degrees. This 90-degree rotated beam is forcefully rejected by the Brewster window. This effectively blinds the mirror and drops the Q factor of the cavity to 0. Cutting voltage to the Pockle cell instantly clears the polarization trap. We are damming and releasing physical light through the manipulation of electric fields. While QSwitching operates in the nanosecond regime, probing molecular dynamics requires pulses measured in femtoseconds. A real laser crystal amplifies light across an entire curve of frequencies, shown here as a gain bandwidth. Within this curve, the optical cavity allows thousands of discrete standing waves to oscillate, spaced equally by the speed of light divided by twice the cavity length. In a standard continuous wave laser, these thousands of modes oscillate with completely random, uncoordinated phases. This microscopic chaos results in destructive interference, averaging the output into a constant noisy baseline that hides the system's true potential. Mode locking forces all of these independent longitudinal modes to share a fixed, synchronized phase relationship. Through Fourier synthesis, 3 out-of-phase sine waves sum into a low-amplitude ripple. When mode locking aligns their phases, they constructively interfere, transforming the sum into a massive vertical spike. This pulse duration is mathematically defined by the locked mode count and their frequency spacing. This creates an inverse relationship. The wider the bandwidth and the more modes locked, the shorter and more intense the resulting pulse. Mode locking does not store energy over time. It mathematically stacks frequencies on top of each other, creating structures of light measured in femtoseconds. We bypass the steady-state limit either through macroscopic storage or microscopic synchronization. QSwitching relies on loss modulation, yielding nanosecond pulses optimized for massive raw pulse energy. Mode locking relies on phase synchronization, producing femtosecond pulses optimized for extreme peak intensity and high repetition rates. QSwitch technology provides the brute force required for heavy industrial applications like laser ablation and material processing. Mode-locked technology provides the exact temporal resolution necessary to freeze and probe electron dynamics on the attosecond scale. By mastering the geometry, polarization, and phase relationships within the optical resonator, engineering transforms a steady beam of light into the sharpest, most powerful tool in modern physics.